Okay, folks, the last topic we're talking about for chapter 6 is something called photoelectron spectroscopy. This is our way of gathering experimental evidence that supports the whole SPDF orbital sublevel idea of the atom. So all of these electron configurations were actually just a theory until very recently we were able to develop experimentation techniques that prove to us that we got this right and we know where the electrons are located within the atom. So in order to read these graphs, I first have to explain a couple concepts. First, you have to remember that in the nucleus are a bunch of positive protons, and these electrons are negative, and we know that positive attracts negative, okay? Something else to keep in mind is that these shells get farther and farther away from the nucleus. So the closer you are together, the stronger that force of attraction is going to be. So if I wanted to compare this electron versus this electron in terms of how strongly they're being attracted to the positive protons in the nucleus, this electron is definitely going to be more strongly attracted because it's much closer to the nucleus. Meanwhile, this guy is going to be having less attraction to the nucleus comparatively because it's so far away from the nucleus. So the way that we've come up with a way to test this is we'll send a high energy beam of, usually it's an X-ray beam, and we'll make sure we pay attention to the energy that it emits. So let's say that we shoot a beam of energy that's 10 kilojoules of energy at this electron located here in the atom. If it's strong enough to break that force of attraction, the electron will be ejected from the atom, and with any leftover energy, it'll be flying at that speed. So let's say that this is flying at a speed of 3 kilojoules when it's ejected from the atom. If it was hit by 10 kilojoules of energy and then is shot out with only 3 kilojoules of excess energy, that means that the energy of attraction, the energy that kept it bound to the atom, was a difference of 7 kilojoules. So that means the energy of attraction, which they call binding energy, for this particular example would be 7 kilojoules, okay? Meanwhile, if we did the same thing, if we shot this guy with 10 kilojoules of energy and we ejected it from the atom, would you expect it to have more or less energy? It would have more. Let's say this guy has 5 kilojoules. That would tell us that this electron is only bound to the atom with 5 kilojoules of attractive energy. Okay, so between these, this would be a 5 kilojoule binding energy. And then let's do the same thing on here. If we shot 10 kilojoules of energy at this outermost electron and ejected it, this guy we could expect to maybe fly out with 10 kilojoules of excess energy, meaning it had binding energy of just 2 kilojoules. Okay, so that's our way of that was the theory behind this development method. Okay, to give you a better idea of what it looks like, I have a little animation here. It looks like this. Okay, so in this animation here is a source of lithium. Okay, there's 3+, I know it's kind of hard to see. And each lithium has its electrons on either an inner shell or an outer shell. Okay, keep in mind that the inner shell electrons are going to be more tightly held and the outer shell electrons will be less tightly held. So take a look at what happens when we shoot some X-ray sources at these electrons. You guys are going to find the data being collected up here. So pay attention to what electron is being ejected, if it's an inner or an outer shell electron. Here we go. So that was an inner shell electron. There's its binding energy. That was an inner shell electron, but it missed the analyzer, so we don't get data from that one. I believe this one was an outer shell electron. That's an inner shell electron. This one, another one, was an inner shell electron. And that's an outer shell electron. And another outer shell, but it missed the detector. And I believe that was an inner shell electron. Okay, so that's the data that we would get. So take a look at that binding energy up here. the 6.26, that's your higher binding energy. The lower, the scale is just weird because it's high up here and then it goes to lower. The same thing is in our notes. If you guys take a look at our notes, a couple things I want to share with you guys about what that looks like. If we look at this PES diagrams, photoelectron spectroscopy, this is the PES diagram for, I believe, nitrogen. Okay, nitrogen has 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. So a couple things to note. Notice the binding energy is on the bottom. This is your binding energy, and it starts high and it goes low. Okay, so your stronger binding energy, weaker binding energy. So take a look at how these peaks can be labeled. This is your 1s2 peak, 2s2, 3, 2p3. Please note the size of the peaks. Okay, there are 2 electrons at the 1s2 level, 2 electrons at the 2s2 level, and then 3 electrons at the 2p3 level. Also notice that as we're going farther out of the atom, we're getting weaker binding energy. Okay, so that is how you label these PES diagrams. You basically figure out the electron configuration and then start labeling your peaks. Okay, so that being said, take a look here and take a guess what atom you think this is. You should be able to figure out what type of element we're looking at based on this PES diagram. And if you need help figuring it out, label the peaks. This is going to be your 1s2 peak, 2s2, and then this would be 2p5. Okay, I know it's 5 because take a look, 5. Okay, so 2p5, let's find where that is on the periodic table. 2p5 is going to be 1, 2, 3, 4, 5. This was fluorine. Okay, let's keep looking. Let's look at this one. So let's figure out what element this is. If you want to pause and try and figure it out yourself, go for it. All right, let's go ahead and figure this one out. This one is going to be 1s2, 2s2, 2p6, 3s2, and then 3p1. I'm just doing this in order, you know, the order of the periodic table, right? So 3p1 is aluminum. Al. Boop. Okay. Go ahead and figure this one out, folks. All right, we've got 1s2, 2s2, 2p6, 3s2, and then 3p5. 3p5. 1, 2, 3, 4, 5. This was chlorine. Okay, so the only other kind of question you might get about these type of diagrams is something like this. I want you guys to notice something important. Look at the 1s2 peak. For nitrogen, it had a binding energy of 39.6 megajoules. And then fluorine, it got stronger. Aluminum, even stronger. Chlorine, even stronger. So we're noticing the binding energy of actually all of these peaks is growing. Okay, and I want you guys to realize why. We had nitrogen, fluorine, aluminum, chlorine. Here's nitrogen, fluorine, aluminum, chlorine. Do you guys notice that for each of the examples, we're adding more protons to the nucleus? Okay, so we have 7 protons, 9 protons, 13 protons, 17 protons. So the more protons you add to the nucleus, the more strongly the electrons are going to be attracted. And so you're going to see an increase of binding energy the more protons you have. So that's why we see these peaks moving a little bit based on what element you have. So the 1s peak will not always be the same between elements. Okay, within an element, it'll be the same, but comparing nitrogen to fluorine, we should expect to have fluorine be a stronger binding energy for all of its electrons because it has more protons. Okay, and that is PES.